Hi everyone. In this video I'm going to introduce you to the Taylor series. We'll look at why it's needed, how to derive it, and how to use it to approximate a function at any given point. To understand why it is needed, we can consider y equals e to the x, which is this red line here. The blue dotted line is the Maclaurin expansion of e to the x, which you can see here. And you can see that the Maclaurin expansion is a very good approximation for e to the x when it is centered on 0. However, as x gets bigger, we can see the Maclaurin expansion becomes less accurate as an approximation for e to the x. Say for instance when x equals 5, you can see the blue dotted line is now quite far away from the red line e to the x. So the Maclaurin expansion is not a good approximation for e to the x at this point. What the Taylor series does is to allow us to center the expansion onto any given x value. In this case, when x equals 5. We have our Taylor series here in green, and you can see it has shifted the expansion, so when x equals 5, it is a very good approximation for y equals e to the x. But again, as we go away from this center, it becomes less good the further we go away in both directions. Okay, so let's look at how we derive the Taylor series expansion. So here we have a Maclaurin series given as a function g of x, and we've been asked to show that a Maclaurin series cannot be used to approximate the natural log of x. So if we go back to our series, you can see the first thing that we need to do is to substitute 0 into our function, but then the natural log of 0 is undefined. Also, if we were to look at the first derivative, well then that would be 1 over x, and to substitute in x equals 0, again that is also undefined. So we know the Maclaurin series is a good approximation when it is centered on 0, but there are some functions, such as the natural log of x, for which it can't approximate. To help us overcome this, we can use the Taylor series. So we talked about previously how it shifts the function. Well, we can shift the function to any general point by letting f of x plus a equal g of x, and then we can substitute this in place of g of x. So we get f of x plus a is equal to, we can see at this point that x is 0, so if x is 0, we can substitute 0 into here, we get 0 plus a, so this becomes f of a. And if we were to differentiate g of x, that would be the same as the derivative of f dash x plus a. So our next term becomes f dash of x plus a, but x is 0. So it becomes f dash of a, multiplied by this x. If we were to differentiate it again, we get f double dash, and we know x is 0, so 0 plus a, and it becomes f double dash of a times x squared over 2 factorial. The next term, f triple dash of a times x cubed over 3 factorial. So the general term becomes f to the power of r of a over r factorial times x to the power of r. Okay? So this is one form of a Taylor series. But if we go back to our original function, we've shifted Maclaurin expansion across, but now we can shift it back. And to shift it back, we can say let x now equal x minus a. So we're going to substitute x minus a into each x value. So if we put it into here, then we get f of x minus a plus va. These a's will cancel, so we're left with f of x. And then we can say this is equal to f of a plus f dash of a times x minus a plus f double dash of a. Again, we can replace this with x minus a all squared over 2 factorial. So we'll carry this on, and our general term will become f to the r of a lots of x minus a to the r all over r factorial. Okay, so I hope this has given you an idea of how we create the two different versions of the Taylor series. In this video, we're going to look at both of them, but we're going to focus most of our efforts on this series, which I think is just a little bit more easy to use. In our next example, we're going to use the Taylor series to approximate a square root function. Okay, so in example 1, we've been asked to use the Taylor expansion to express the square root of x plus 1 and ascending powers of x up to a term in x cubed, and then to find an approximate value of the square root of 1.2, given our answer as a fraction, where we need to find the values of a and b. Okay, so if we're going to look at x to the cubed, then we're going to use our first equation. So this means we're going to need to find the derivatives of our function. So if we say f of x equals the square root of x, or x to the half, well, we can find f dash of x by differentiating this. We'll bring this power down, and then we'll take away 1 from the power, so a half x to the negative 1/2. The second derivative will be f double dash. Again, we'll bring this power down, and then we'll take away 1 from the power, so we get negative 1/4 x to the negative 3/2. And then for our third derivative, we'll have f triple dash. We'll bring this power down, and then we'll take away 1 from that power, so we get 3/8 of x to the minus 5/2. So now we've got our derivatives, we need to substitute in our a value. In this case, a will be equal to 1. So we'll find f of 1, which is 1 to the half, so just 1. F dash of 1, well, this becomes 1 times by a half, so 1/2. Again, this becomes 1, so we get negative 1/4. And for our third derivative, we get 3/8. So now we've got this term, this one, and this one. We can substitute them into our equation. So f of x plus 1 is approximately f of a, which is 1, plus f dash of a, which is a half, multiplied by x, plus f double dash of a, so negative 1/4, of x squared, all over 2, factorial, which is 2, plus 3/8, which is this value, x to the 3, over 3 factorial, which is 6. And we can simplify each of these fractions, so our approximation becomes f of x plus 1 is 1 plus a half x minus 1/8 of x squared plus 1/16 of x to the 3. So this becomes our Taylor series approximation for f of x plus 1. And in example B, we've been asked to find an approximate value of the square root of 1.2. But now we can say, if we let the square root of 1.2 equal the square root of x plus 1, then we can use our expansion. So if 1.2 equals the square root of x plus 1, we can square both sides, so 1.2 is equal to x plus 1, and then our x value will be 0.2. So now we can substitute 0.2 into our expansion. So f of 1.2 will be approximately 1 plus a half minus 1/8 of 0.2 squared plus 1/16 of 0.2 cubed. And we can work this out on our calculators, and we get f of 1.2 is approximately 1.0955. Okay? And in example 2, we're going to look at applying both equations to find the expansion of tan of x. Okay, so for our final example, we've been asked to use the Taylor expansion to express the tan of x plus pi over 4 in ascending powers of x up to the term x cubed, using equation 1 and then using equation 2. And then we've been asked to find an approximation. So the first thing we need to do again is we need to find our derivatives. Well, if f of x equals tan of x, then we know the standard derivative becomes sec squared of x. And now to work out the second derivative, well, we can use the chain rule. If f of x is sec squared, we can write this as sec of x all squared. So our second derivative then, we can bring this 2 down, so we get 2 sec x, and then we can multiply this by the derivative of sec x, which is sec x tan x. So our second derivative becomes 2 sec squared of x tan x. So to work out our third derivative, we need to use the product rule. If we say 2 sec squared x is u and tan x is v, this will be u times dv, which is sec squared x, plus v tan x du. And we've already worked out the derivative of sec x here. So we multiply this by 2, and it becomes 4 sec squared x tan x. We can tidy this up, so f triple dash of x becomes 2 sec to the 4x plus 4 sec squared x tan squared x. So I'm just going to delete all of this working out so we've got space. Okay, so we've worked out our derivatives. Now we need to center it on pi over 4. So we'll say a is pi over 4. So f of pi over 4. Well, we know tan of pi over 4 is 1. We know sec x is 1 over cos x. And cos of pi over 4 is 1 over root 2. So sec of pi over 4 will become root 2, and sec squared will become 2. So if we go back to our derivatives, we know f of pi over 4 then is 1, f dash of pi over 4 is sec squared, which is 2, f double dash of pi over 4 is 2 sec squared tan x, so 2 times 2 times 1, which is 4. And for our third derivative, we get sec to the 4, which is the 2 squared, so 4, times that by the 2, plus this 4, times sec squared, which is again 2, times tan squared. So this becomes 8 plus 8, which is 16. And now we can begin to substitute each of these into our formula. So if we use equation 1, we know that f of x plus pi over 4 will be equal to f of a, so 1, plus f dash of a times x, so plus 2x, and then f double dash of a times x squared, all divided by 2, so 4x squared, all divided by 2, and then a third power, f triple dash of a divided by 6, which is 3 factorial, which gives us 16 over 6 x cubed. And we can simplify each of these fractions. So we get f of x plus pi over 4 is equal to 1 plus 2x plus with 2x squared plus 8x over 3 x cubed. So this is the approximation for f of x plus pi over 4 using equation 1. So for question B, we need to look at using equation 2. So now we have f of x. We still know that a is pi over 4. So we want f of pi over 4, which we know is 1. And then f dash of a, which we know is 2. And now we have x minus a, which is x minus pi over 4. Plus f double dash, so 4 over 2 factorial. So lots of x minus a squared, so x minus pi over 4 squared, plus f triple dash of a over 6, which we know is 8 over 3 x minus pi over 4 cubed. But the question wanted ascending powers of x up to the term x cubed, not x minus pi over 4 cubed. But we're trying to work out the tan of x plus pi over 4. So we need to let this x equal x plus pi over 4. And this will shift the function back. So if we were to substitute x plus pi over 4 into here, well, this negative will cancel with this positive. And the same will be true in this bracket and in this bracket. So what we get then is f of x plus pi over 4. We've substituted this into here is equal to 1 plus the 2x, again because this has cancelled with this one, plus 2x squared plus 8 over 3 x cubed. And this is exactly the same as what we've got here. Okay, so finally for question C, find an approximate value of tan of 48 degrees, given your answer in terms of pi. So we know that pi over 4 is equal to 45 degrees. So if we've got x plus the 45 degrees, then x must be 3 degrees. And in radians, 3 degrees is equal to pi over 60. So all we need to do is substitute x equals pi over 60 into our expansion. So f of pi over 60 plus pi over 4 is equal to 1 plus 2 lots of pi over 60 plus 2 lots of pi over 60 all squared plus 8 over 3 times pi over 60 all cubed. So we get 1 plus pi over 30 plus pi squared over 1800 plus pi to the 3 over 81,000. Okay? So I hope you found that useful and that's given you a better idea on how to use and derive the Taylor series. If you did find that helpful, please like and subscribe, and you can download the full lesson and worksheet from my website missmathematics.com. There's a link in the description below. Thanks for watching and take care.